Hi, I'm Jim Lake. Over the past several years, I've had the privilege of being able to work with a number of friends in the RC airplane hobby, and I've worked with them and watched them fly their RC planes. I've noticed during this time that there were a great number of accidents, most of which appeared to be result from a stall. And in many cases, the stall was unrecoverable and the airplane was lost. Now, I've been a pilot of airplanes and helicopters for most of my life, and I realize that full-scale airplanes can't operate without an airspeed indicator, and it's an essential piece of equipment. I noticed, however, that no one in the RC hobby world produces an airspeed indicator that's useful and easily incorporated into RC planes. I realized there had to be a better system, and over a period of about 18 months I've developed several of them. The first one being an angle attack system, which worked, but we eventually discarded because we found that there was really no convenient place on a single engine RC plane to be able to put the vane that detected the relative wind. I also tried a traditional pedostatic system that had been scaled down for RC planes. This also worked, but it didn't work very well because the airspeed readings contained so much noise that by the time the data stream was output to the receiver, the airspeed indications were essentially useless. Finally, I decided that we would try to work with a fan-based or an impeller-based system somewhat similar to what you might see in a wind meter. And in doing this, we developed what is presently the LMAS system. We needed a system that would be reliable at low airspeed, that would be reasonably inexpensive, and would allow the pilot to receive the airspeed information without having to take his eyes off the airplane that he was flying.
The LMAS system consists of three principal parts: the sensor, the remote transmitter, and spoken link, the user interface. The sensor is a small, lightweight, impeller-based device that measures the speed of the air moving through it. It's powered by any DC voltage from 5 volts to 37 volts. For best results, the sensor should be installed at a location in the aircraft that has access to the undisturbed flow of the relative wind. For example, the leading edge of the wing outside the propeller arc. The sensor can be installed remotely and the airflow directed to it through a flexible airflow tube. The remote transmitter is an extremely lightweight 900 MHz spread spectrum radio transmitter receiver called an XB. It's fully certified by the FCC and has a line of sight range of up to 4 miles. Spoken Link receives airspeed data from the remote transmitter and converts it to voice. It speaks the airspeed using earbuds or a powered speaker every 1.7 seconds. It also has the capability to store a stall speed and provide a timely warning when the aircraft approaches stall. The LMAS radios are paired with one another and cannot interfere with other radios or an RC transmitter. Spoken Link will fit in a pocket. It's powered by a 9-volt alkaline battery.
The preferred location for the LMAS sensor is in a cavity in the wing behind the leading edge and outboard of the propeller arc. The sensor can be mounted by gluing a 3/8 inch ID brass or carbon fiber sleeve through the leading edge. The sensor can then be inserted into the sleeve and fixed with hot glue. The intake tube of the sensor can be left extending from the leading edge to simulate a gun, or it can be trimmed flush. The remote transmitter can be installed remotely
for example in the cockpit, and the interconnect run from the sensor to the radio. This way, the radio can be moved between aircraft, each having its own sensor installed. Alternatively, the radio can be installed in the landing gear bay and secured with Velcro. As always, be sure to observe the correct polarity for the wires in the interconnect. An excellent method of installing the LMAS system on multi-engine aircraft is in the nose cone, demonstrated here installed in the nose cone of an ME-110. In this case, the nose cone has gun ports that can accept a glued-in 3/8" sleeve. The sensor can be slipped into the sleeve and secured. The nose cone is also an excellent location for the remote transmitter. As in the wing installation, the intake tube can be left extending from the gun port, or it can be trimmed flush with the surface. There are many other creative ways to install the system in single-engine aircraft to ensure it receives undisturbed airflow. It's shown here installed in the wheel pant of a 118" Lysander. The intake tube has been left flush with the surface of the wheel pant. The sensor has been installed in a 3/8" flexible tube glued into the inside of the wheel pant. The remote transmitter is velcroed below the sensor. The power source and switch are in the fuselage where they're accessible. The cover for the unit is the section of the wheel pant cut away to make the opening. The LMAS system can also be installed as an integrated system within an external container such as a bomb or a drop tank. It's shown here installed in a 1/5 scale bomb. This installation has all the necessary components within it, including a battery. Accordingly, it can be moved between aircraft without modification. LMAS is another innovative electronic system brought to you by Microsystems.